Welcome to the Math Record. Today we'll be learning about the properties of complex numbers and the Moivre theorem. This video will cover part 2 of chapter 8 in our Precalculus class. Okay, let's get started. The first thing we need to learn is how to find the products and quotients of complex numbers. So imagine you have a complex number like z is equal to 2 cosine of cosine of 5 plus I sine of 5, right? We'll be using degrees right now, okay? So that's your first complex number. And you have another complex number, which is z of 2, and we'll say that is 4 cosine of 40 plus I sine of 40, right? And these complex numbers are in their polar form, basically. What it states is if we want to find the product of like complex number 1 times complex number 2, which is just z1 times z2, basically you will have to multiply the magnitudes. So, and then you had to like kind of add the angles. So it's be cosine of angle 1 plus angle 2. Um, put that in parentheses. Plus plus I sine of the same angle. So angle 1 plus angle 2, basically. Sorry, I'm running out of space. So basically, if you want to multiply angle 1, 2 cosine of 5 plus I sine of 5, and angle 2, 4 cosine 40 plus I sine 40, it's 2 times 4, which is 8. And then adding the cosine, which is 40 plus 5, which is 45. So you have cosine of 45 plus I sine of 45. Because these two angles are probably the same. Cosine the same, and the sine will basically be the same. And then you could kind of just like convert it into like basically a rectangular form. So cosine of 45 is square root 2 over 2. Sine of square root 45 is square root 2 over 2. So 8 times cosine of 45, which is square root 2 over 2, is basically 4 square root 2, plus I sine of 45, which is square root 2 over 2 times 8, which is the same thing, which is 4 square root 2. So magnitude 1 times magnitude 2 is 4 square root 2 plus I times plus I 4 square root 2, which I times 4 square root 2 is just basically the imaginary portion. So that's basically how you do it. And this basically works for anything. This is the basically the general form. So let's say like instead of saying this is like 5, right? We could say this is say this is 20, right? So if this was like a cosine of 20 plus I sine of 20, we have z1 times z2, which is now 8. And then cosine of 20 and cosine of 40, that makes cosine of 60. And then I sine of 20 plus I sine of 60, that would just make the same thing as I sine of 60, basically. Using the general idea, which right here. So then cosine of 60, which is basically just 1/2. And I sine of 60 is just basically I squared root 3 over 2. So this will get 4 plus I 4 square root 3. Which is basically how you do it. So that's how you do like the products if you're multiplying like two of the vectors. And now let's have like let's find out how we like divide not vectors, complex numbers. Now let's find out what happens when you divide complex numbers. So let's say you have magnitude 2 divided by magnitude 1. This is basically for the magnitude I mean complex number 2 divided by complex number 1 would be the magnitude of the second one divided the magnitude of the first one all over cosine times cosine of the second angle minus the first angle. Sorry, minus. And then plus I sine in basically the same angle. And you have angle 2 minus angle 1. Basically. So let's say you have the angle 2 divide, not angle 2, complex number 2 divided by complex number 1. So 4 divided by 2 is 2. And cosine of 40, So the 40 minus the 5 is 35, which is cosine of 35. Plus 40 minus 5, so that's also 35. It's going to be the same all the time. The angle is going to be the same. So plus I sine of 35, basically. And then you could like put this into like decimal using your calculator, and you could multiply this out to rectangular form. So these are the general form of finding out the product and the quotient. So what we usually do is that you find the rectangular coordinate, is the rectangular coordinate, and then you convert it to the polar form. And then the polar form, you use this these properties, and then you get the answer, and you convert it back to a rectangular form. So the next thing we're gonna be learning is gonna be the De Moivre theorem. So I'm probably might be mispronouncing it, but it's called the sorry, the De Moivre theorem, which basically helps us find something like, let's say you have 1 plus like I square root 3 to the I square root 3 to the power of 5. Okay, so you want to find something like some kind of complex number, which is imaginary, raised, or I mean like basically a complex number raised to a power, basically. So well, let's say we denote this as a z, right? Basically, so what it states is that if you have complex number z and you want to raise it to the power of n, then it states that if you write the complex number in its polar form, then this z to the power of n, which is like the complex number raised to that power, will get to the magnitude, which is r raised to the power of n times cosine of the angle, which we will call theta, times n, plus I sine of the theta times n. So that's basically what it is. So let's say we have something like as our example before. So we have like 1 plus square root 3, 1 plus I square root 3 raised to a power of, let's say 4, right? Then converting 1 plus I square root 3 to polar form, the magnitude is basically 1 squared plus square root 3 squared, which is just 4, and then square root that is 2. So the magnitude is 2. So parentheses 2. Uh, so factoring the 2 out, you get 1/2 plus I square root 3 over 2. I square root 3 over 2. That's raised to the power of 4. Now, if you think about it, now you have something like right here, right angle. And then the cosine, this would be the cosine because you have to put in the polar form. This would be 1/2. And this is square root 3 over 2. So basically you want to find theta. So using your calculator, and you could use trigonometry, you find out that theta is going to be like 60 degrees. So you're going to write this as basically equals to 2. Sorry, we're going to need more room for this. Which is 2 cosine of 60 plus I sine of 60. This is 60 degrees in between. And then you gotta raise that to a power of 4. So now you're gonna have this, which is in polar form, which now you can use De Moivre's or De Moivre's theorem. I call it De Moivre. I might be mispronouncing it. So magnitude, which is 2, raised to a power of 4. And then cosine, the original angle is 60, and n is 4. So 60 times 4 is 240, plus I sine of 240. Let me move this up a little bit. Now, this will simplify to 16, and cosine of 240. If we kind of draw the graph out, basically, so this is 180, right? So you gotta make an angle right here. So you have an extra 60 degrees right here. So 80 plus the 60 is 240. So that's what you're gonna get. So 60 degrees. So since this is in the third quadrant, both of them are negative, and the opposite of the 60 degrees is square root. If this is radius 1, right, and it's a right triangle basically, this is square root 3, negative square root 3 over 2, and this is negative 1/2. So basically, cosine of 240 degrees is negative 1/2 minus I, which is, and then sine of 240 degrees is negative, plus I is negative square root 3 over 2. So this kind of simplifies to negative 8 plus, alright, minus 8 square root, minus I 8 square root 3. Because you usually want to put the I first and then you put the number. It's just I times 8 square root 3. You don't, like, you could write 8 square root 3I, but it's sometimes, it's just weird it's just weird notation, because sometimes people might think that, like, the I might be in the square root, but if you put it just under the 3, then they'll understand. But just to, like, make sure that they don't misunderstand that the I is outside the square root, you just put the I in front, and that's basically what it means. It's basically the same thing. It's just 8 square root 3 times I, and so this is the answer at negative 8 minus I, 8 square root 3. If it's you have 1 plus I squared 3 raised to the power of 4, then you'll get this. Instead of doing, like, a bunch of math to, like, simplify it, now you could just use the Moivres theorem to do it. So you get the rectangular, convert it to polar, and then from that polar you use the Moivres theorem, the Moivres, and then you raise that power, you do the operations, and you get the answer basically. And you get, like, that answer, and you kind of return it back to rectangular, and then you get the answer. So that's the Moivres theorem. And the last thing we're gonna be learning is finding complex roots. So like when you have to, like, usually when you get, like, equations like you have an equation, like, let's say y is equal to x cubed minus 8, right? Usually when you find the roots, you only get, like, one answer, right? So if you put this in a graph, what it'll kind of look like is that you have one answer, like you have a graph like this, and this is center at 2. Because if you put 2 in here, that's 2 to the power of 3, which is 8. So 8 minus 8 is 0. So when it crosses the x-axis is 2. So then you get so the only answer of the root is 2. But this is raised to a power of 3. And based on the fundamental theorem of algebra, um, it's it states that there should be 3 roots. So if there's one real root, which is 2, then there's one real root, I'll say r. That means there's 2 imaginary roots. So now we want to find all the complex roots. So we want to find the imaginary roots. And this is the process that we're going to be using, because you're only going to find one answer if you use the regular method. So now to find the complex roots, let's use the same example. We want to find y is equal to x cubed is minus 8, and then when y is equal to 0. So 8 is equal to x cubed. So you want to find the cube root of 8, right? So basically what you're going to be doing is you want to find the cube root of 8. So if you want to find the complex root of a number, so in this case you want to find the cube root of 8, then you have to follow the equation, let's say z, we have complex number, which is z. So we have the nth root of z is basically equal to the nth root of the magnitude times cosine of the original angle plus 360 degrees times n. Not n, times k divided by n, and plus, sorry, I'm running out of space, so I'll just write it on the bottom, plus sine of pi plus 360k all over n, basically the same degrees. So you're going to follow this example. So you want to find the cube root of 8, right? Because you want all 3 roots of 8. What you're going to have to do is that you have to find 3, basically. sorry, you're gonna have to make a sorry. The first step is that you want to make 8 into a into its polar form. Since 8 could just be written as 8 plus 0 I, then technically what you could basically on your polar form, you could just distribute out the 8 because you usually want to get the real number as a constant of 1. So you want to get the magnitude first. So you're gonna have 8 squared plus 0 squared square rooted. That's just 8, right? So the magnitude is 8. So you want to distribute out the 8. So you have 8 1 plus 0 I because 0 divided 0 divided by 8 is just 0. So you have 0 I. So when is this a thing? A 1 plus 0 I. So based on like your complex plane, right? It'll be the real axis and the imaginary. So basically you're gonna have a 1 right here, and then it's just gonna be right here. So based on this, that means this is 0 degrees, right? Because if you go up here, let's say this is like 45, right? Then this is gonna be 45 degrees. Sorry, I put percent. I don't know why. 0 degrees, and you put like right here. That's 45 degrees, basically, and you put like right here. This is 90 degrees. So you understand why it's 0 degrees right here. So this is 0 degrees. So what you write down is that you put this in polar form, which is 8 cosine of 0 plus sine I sine of 0, basically. If you want to use radians, it's also fine too. Just make sure that 360 is also in radians because this is 360 degrees. So if you want to put this in radians, you have to put 2 pi k instead of 360k. So just make sure. I'm just using degrees because it's more common and it's easier to work with because like radians just work with 2 pi and it's not really divisible by a lot of things. 360 is divisible by a lot of numbers, so I just use 360 a lot. So basically, now we want cube root of 8, and 8 would just be the same thing as 8 cosine of 0 plus I sine of 0. So now we're gonna since the magnitude is 8, we're gonna find the cube root. So the cube root of 8 is cube root of 8 cosine of 0 plus 360 degrees times k divided by n, which is 3 plus sine of 0 plus 360k divided by 3. So what it states from this theorem is that if n is equal to 3, you gotta find out what this equals to when k is equal to 0, 1, and 2. Basically. So you have to be 1 less than n. So 1 less than n, which is 3, minus 1 is 2. So you have to find out up to 2. So 0, 1, and 2. So let's just say, like, if we didn't want to find the cube root of 8, we want to find the square root of 8, so it'll be 2 square root 8, so it's 2. You only have to find when k is equal to 0 and 1. Also, if you want to find, like, the fourth root, so 4 roots of 8, you have to find when k is equal to 0, 1, 2, and 3. You see how that works? Because you always start with 0, and then you have, like, and since all these have the same amount, then basically it's just 1 minus this 1. So then you have 1 root. This is k is equal to 0 is 1 root, k is equal to 1 is another root, k is equal to 2 is another root, and k is equal to 3 is the final root. So now you have 4 roots in total. So that's how you do it. So you just follow. So you just plug in the values for k, if you know how that works, basically. So basically you're gonna, since you have the cube root of k and it's equal to 3, so you plug in k is equal to 0, 1, and 2. Because you find out when the root is 0, when the root is 1, and when the root is 2. So that gives you all 3 roots. So, if you plug in k is equal to 0, right? So 360 times k, which is 0, is 0. So 0 plus 0 is 0. Divided by 3 is also 0. So it'll be cosine of 0 plus I sine of 0. So the first, and then cube root of 8 is 2. So it's just 2 cosine of 0 plus I sine of 0. Which is basically cosine of 0 is just 1, I sine of 0 is just 0. So basically this gets us the answer of 2, right? Because if you distribute it out. So this would be our first answer, 2. Alright. So the first answer is 2, right up here in this box. I'm just gonna write it 2 here. right? So that's our first answer, 2, which is already correct because the cube root of 8 is 2. And that's one of the answers. If you put y is equal to x cubed to the power of 8. So y is equal to x cubed to the power of x cubed minus 8. You plug in 2 and you get 0. So that's already true. And the next answer, so that's when k is equal to 0. So now we have to find when k is equal to 1. So when k is equal to 1, it's just 2 cosine of 360 times 1 is 360 plus 0 is 360. So 360 divided by 3 is 120 plus I sine of 120. This is basically the same angle. So now 120 degree, cosine of 120 degrees would be negative 1/2. And sine of 120 degrees would be square root 3 over 2. So 2 times negative 1/2 will be negative 1 plus I square root 3, because square root 2 divided by 2 times 2 is square root 3. So that's the second answer. Let me delete this. And the 1 and the number right here. Okay. So our second answer is negative 1 plus I square root 3. So that's our first imaginary number. And then we have to plug in when k is equal to 2, which is our final one. So that would be 2 cosine of, so 360 times 2 is 720. 720 divided by 3 is 240. So you have cosine of 240 plus sine of 240. So cosine of 240 is basically in the third quadrant, also making a 60 degrees. So what it's gonna make is so both of these are gonna be negative. So this would be negative 1/2, and this would be negative square root 3 over 2. So multiplying it out, you get negative 1/2 minus I square root 3. So that's the third answer. So the three answers are 2, negative 1 plus I square root 3, and negative 1 minus I square root 3. You can plug this in your calculator and like raise it to the power of 3, and you know it's gonna be correct because negative 1 plus I squared 3 raised to the power of 3 should equal 8. And if negative 1 minus I squared 3 raised to the power of 3 is also 8. So that's how you know it's the correct answer. So those are the complex roots, and that's basically how you find it. So that's basically the process. So you want to find the fourth root, you just put 4 here, and then you divide by 4. Usually what I do, instead of like doing the big math, so like 360 times 2 is 720 divided by 3 is 240, like that's such big numbers, what I'll do is I'll separate it into parts. So wherever the original angle is, I just divide that by that number. And then, right? And then, because I don't want to write 0 first, let's say in general theta, right? So, no, never mind. I'll just use this case right here. You have theta plus 360k or 360k divided by n. So you have theta over k plus 360 over n times k, right? This is the same thing basically. I just distributed it out. So what the first thing I'll write is when k is equal to 0, right? So that just means 360 over n times k, which k is 0, so this is 0. So the first angle I'll write is just pi over n. And then the next angle I'll write is just 360 divided by n bigger. Because it's gonna just be like when k is equal to 1, k is equal to 2, k is equal to 3. So what I'll do is that like from this case is that I know the first angle is 0, right? 0 divided by 3 is 0, so I'll start with 0. And then 360 divided by 3 is 120. Sorry. It's 120k. So I know I have to keep adding 120 every single time. Since I need to find 3 roots, that means I need to find 2 more. So from 0, you add 120, so that gets 120. So that's 0 degrees. Sorry. And then 120 degrees. And then from 120, you have to add another 120. Because that's when k is equal to 2, so you just add another 120. So that makes 240 degrees. Right? The cool property about complex roots is that if you go around again, you'll get the same number as the beginning. So you have 240, right? And you add another 120. That's 360 degrees. But 360 degrees is the same thing as 0 degrees. Right? So it kind of gets like this balanced circle. this kind of like balance like number. So you start at 0, you go 120, and you get another 120. So this angle made is 120, right? This angle to this angle is also 120, and this angle to this angle is also 120. And that's when it's cube root. If it's like to the fourth root, right, it's just gonna get this angle, then to this angle, then to this angle, and then to this angle. So it makes a 90, a 90, a 90, a 90. Just think about it. It's just 360 divided by 4, because you have to find the fourth root. So now you have, all of them are 90 degrees in between. So that's a really cool property about it. So in this case, like, let's just show it like another example, right? Let's. I'm not gonna do all that math again, but I'll show you another way. So let's say we have something like the fourth root of 8, right? So you have 0 plus 360k divided by 4, and you have to find all the 4 like angles. First, you just write 0, because 0 divided by 4 is 0, and 360 divided by 4 is 90, so it's 90k. So to add 90 to get the second angle, add another 90, which is 180 to get the third angle, and you add 90 to that to 180 to get 270 to get the fourth angle. So those are all the 4 angles. And you add 90 to the 270, you get 360, which is 0. So you get back the first angle. So that's basically how you do it. So these are all 4 complex roots. When cosine is 0, when cosine is cosine 0 plus sine is 0, I sine is 0. And then you have cosine of 90 plus I sine is 90, and then cosine of 180 plus I sine 180, and cosine of 270 plus I sine of 270. And based on like what's the fourth root of the magnitude. And that's basically how you find the complex zeros using polar. So so in summary, in this video we learned about how to multiply and divide complex numbers, and we learned about the De Moivre's theorem, which is basically raising a number to a power, and we find out how to find complex zeros, which is basically just finding the roots of a complex number. So thanks for watching, and I'll see you at the next math record.